Well, it looks like we could get started. Welcome back, everyone. This is always a tough week because we are in the middle of midterms week, but we're definitely getting through it. If you feel a little tired today, I totally understand, but any questions at the moment to get us started? Okay, where we're at so far, we're on example 3 on section 11.1 on sequences. We may get through this section today, so we have section 11.2 lined up. We'll probably be working on that one tomorrow as well. Also for the announcements, our second exam is coming up, like we mentioned, next Monday, only for these particular sections. So if you do have any questions when we come back to class on Thursday, don't hesitate to ask. I'll be happy to help out. Also over the weekend, if you're working on studying, I'll be very available on Friday, available on Monday. And I always check my emails, even on the weekend in the morning. So send questions as they come up, and I'll definitely get to them on the morning for sure. Because it's an exam week, I'll be checking my email a little bit more often than normal as well. So far, we're going to go through our section on sequences, but any last questions, folks, on the announcements? Okay, let's see where we left off. We left off here. This was our example of what looks like a divergence sequence. We were only to calculate the first 5 terms, but we made this a bigger problem and used technology to calculate the first 20 terms. And we see a definite pattern. AN is referring to each of the terms of the sequence. If you plug in a 1, the value looks like it's just above 2, plotted as that point. But as the index n goes this way, larger and larger, the value of the nth term, a sub n, gets higher and higher. And so we said overall, the limit is infinity, so this is a divergent sequence. So that's what we're going to be working on in this section, just getting a better handle on when these limits exist and when they fail to exist. We put here just a reminder, this is very similar to section 2.6, practically a review on it. So even just scanning over that section is very helpful for this material. Any questions with this problem here? Okay, going forward, here's the harder problem that we mentioned. What we did before was we had a formula for the nth term of the sequence, and this time that formula is missing, so we're going to find it. And all we know is the first 5 terms printed here. Now, this is a kind of interesting question because there's a lot of sequences that could fit to any 5 terms you give. There's lots of patterns that could work out with that data. What we're looking for is just the most obvious pattern. So the thing that you would stumble on first when you're trying to get a formula to fit all of those terms. It is a kind of a weird science where you're building things from scratch, kind of trial and error. So think factoring trial and error. That's not too different from what we're doing here. What we do is we start off by just guessing the form of AN based off what we see. So the first thing to note is, well, there's some really strange constants, but it does start off as positive, then goes negative, positive, negative, positive. So we can say that this is an alternating sequence. What's alternating is the positive, negative signs. And that part's not so bad. If your sequence is alternating, we take -1 to the right power. And the way we decide on the power is just whatever the first term is positive or negative. So if we go like this, AN, then we test this out. A1, that means we're trying to find out if A1 is going to come out positive. We need +4, but we're first resolving if it's positive. We're plugging 1 there, and that would just give us a -1. A negative sign to an odd power is always negative. So that didn't work. We just build off it. Go +1 instead. So now if we plug 1 inside here, we have -1 to an even power. We're squaring -1. That would come out as a +1, which is what we're gunning for. So we are just 1 step there. We've got the alternating part down. That's one of the first things you want to take a look at. Any questions at the moment? Okay. Other features of this sequence that we're seeing here is that it looks like powers of 4 are involved. We have 4, then -1, 4 in the denominator, 4 squared, 4 cubed, all in the denominator. So this looks to involve some power of 4 altogether. Getting the power down right is not easy. For example, if we put down just n, it's not going to quite work out. We're always testing this way. Plug in A1. It should give you that term. That's our A1. But so far, if we plug in 1, we get positive here and just a 4. That was meant to be scratch work looking pen. Let me try again. That tells us the power n is not correct, but we're building on this, trying to get it to come out right. Anyone see what the modification should be on that power n? Looking at my work here again, I can tell mine might be a little bit tired as well. We plugged in 1 and we got 4 in this way. That actually looks right. So let's keep on testing this thing. Here's A2. It should come out as a -1. That's where we start to encounter difficulties, right? It looked okay at first because we matched a term, but plug 2 inside this next and you get A2 equals. This will be a power 3, so it's negative. 4 to the power of 2 would give us 16. And now we're way off. We didn't hit A2 at all. So the exponent is still not quite right. And modification is needed. We need to add a power or subtract a power to make this all work out somehow, some way. Anyone see what we should do to that power n?
We should subtract a power, right?
I agree with you, absolutely. So let's see, how about if we subtract maybe 1? Let's go to our scratch work here in orange. If this is 4 to the power n minus 1, plug in 1 here, we get positive. Plug in 1 here, it's 4 power 0, which is 1. That didn't work, so we try something next. I still think you're on the right track. We need to subtract powers. So let's subtract -2 and see what we end up with. So now with this value, again, we're plugging in 1, so that part's positive. Plug 1 in here, it's 4 to the power 1 minus 2. So it's 4 to the power of -1, which is 1/4. Still not quite right, but you know what could fix that? Take that whole 4n to the power n minus 2, drop it to the denominator instead. So it's in this way that this kind of work is really just trial and error. You start building out to your function here, testing it out, make fine-tune adjustments as they come up. So let's start off. I think we're on the right track. So A1, we're going to get positive 1 in the numerator, 4 to the power of -1 in the denominator. When we correct our exponents, we can bump that up into the numerator position. And now it's 4 to the power of +1, which means we landed on 4 on this one. But these are tricky, right? We landed on 4 with the incorrect formula, so we need to keep on checking. Let's see if we get A2. At A2, 2 goes in here, so this is -1 altogether. Since it's to an odd exponent, we plug a 2 here. This is 4 to the power 0, but that becomes equal to -1 exactly, since 4 power 0 is a 1. So we got our A2 turned down. We may check all of them if we're being extra suspicious, but for a lot of these things, usually checking the first 3 is a good call. So let's take a look at A3 next. We're plugging 3 in there, so that's -1 to the 4th power, +1. 3 plugs inside there, so it's 4 power 1. And that reduces to 1/4. So we really do have the right thing. On our next one, this would be A4. Let's just eyeball it this time. 4 in there would give us a -1, so we've got that. 4 in there is a power of 4 squared now. So 4 squared would give us the 16. So it looks like we're in luck with this. Again, you'd want to check at least 3 terms. All 5 terms is the gold standard, but if you feel like you're convinced at this stage with the 3rd term, you're usually probably on the right track. So when it says find the formula for the general nth term of the sequence, that's the answer, but really our work is all of that just coming up with the information to get us to that answer. Any questions, folks, with getting that formula down? Okay, so now that we have that formula, here's another interesting discussion with calculus and another reminder. One thing that makes calculus hard is the notation. It was independently discovered by different people on different parts of the planet when you couldn't have email, stuff like that. And that made the notation wacky just on its own. But it's also kind of a mad science when you're doing sequences in series. The notation can have a lot of extra issues there. So when we write down a sequence like this, 4, -1, 1/4, -1/16, 1/64, and go ... We can also write it this way, an, as n goes from 1 to infinity. This is just saying we have an nth term. Then let me just fix my penmanship here. We have a formula for the nth term, and so we're just conveying it this way. That's where an is. Or we might write it this way. Sometimes you'll see your sequences in the book written out this way, where the nth term is just exhibited. And we give the information, this is valid from n equals 1 to infinity. Or sometimes the whole sequence is like what we put in the answer, just the nth term is given and nothing else. That means there's 4 ways to visualize this: as a function indexed at n, as a set that's infinitely long, and well, I guess these two, that's the third way. Only difference is putting in the function versus leaving it as an. So that's kind of a nasty thing with the notation, but every one different way of visualizing these things comes up routinely. So it's also important to kind of train your eyes to know what you're looking at when you see it. Something that's comma separated is indicating a sequence. That's already a big deal for us, because if something is separated like that with pluses and minuses, that's not a sequence any longer. That's what we mean by a series. So keeping those two topics separate in your mind is super, super fundamental in chapter 11. Think of it in these terms. A series means you're adding together terms. A sequence just means you're listing them, so comma separated. In the next chapter, that's what we're trying to do. Take every term of the sequence and just full on add them together. It would look like this, for example, in a different problem. Well, any questions at all, folks, with the major takeaway of example 3, just producing that function?
So the strategy for that was bang your head against the wall till you figure it out?
That's basically how it goes, yeah. We're going to practice this more and more, but I think that's a pretty accurate way to describe it. For example, just on this problem right here, notice it's red. I put like a million edits on this document, try to choose the right problem. But we have to do the same exact thing. We have to come up with a nth term here of the sequence that produces this series. And it is pretty much that. Reverse engineering by just looking at it in stages. We get better at it with time. Yeah. I would say that's a good start, yeah, because that takes care of the pluses and minuses. So I would always start off this way. Oh, with the, what do you mean by the negative? Yes, correct. Yeah. Other questions at the moment? You could have a bunch. Yeah, I'm glad you mentioned that. So for example, on this one, you could do stuff like factor out some, oh, hang on. There we go. They lagged for no apparent reason. But you could factor out a powers of -1 and make this go -1. Let's make that be power 3, for example. We factor out 3 factors of that. This leaves -1 to the power of n minus 2. 4 is to the power of n minus 2. So some people might have done this as their answer. -1 over 4 to the power n minus 2. And that's a totally correct formula as well, coming from that one. So it all just depends on what strikes you as the most interesting part of the sequence and how you decide to put it together. Your algebraic forms could be a lot different than that one. And probably could be creative with this and come up with different formats too. But other questions about that so far? Okay, for just one more example, that's such an important question because we're going to do a lot of stuff with exponents. So understanding how you could play with these things, move the exponents around, becomes fundamental as well. Here's another weird thing you could do. This could be equal to -1 to the power of n plus 1. And some people may not have put the base 4 in the denominator. They may have kept it in the numerator, and your answer could have been this, 2 minus n. All I've done is I multiplied the exponent by -1 to get a positive 2 minus n, and that formula is equally correct as well. So loads of different ways to write this. That means when I go to grade these problems, I take a lot of additional time because I might sometimes, if a weird form comes up, have to verify it myself if that even makes sense. I might not see that what the connection is from here to here right away. But there could be as many different answers as there are people in class. That's kind of amazing in a way. Other questions at the moment? Let's add just this to the notes. Another valid formula. So just as good as the other. Well, aside from coming up with the nth term of the sequence, other things that we're really interested in is when the sequence converges and when it diverges. That's also pretty important when we're thinking about series, because if we are adding infinitely many terms, the size of each additional term should be getting smaller. Otherwise, the total sum would diverge. So we're next really interested in limits of sequences. And we mentioned before, all of these limit laws, it's kind of overwhelming when you stare at it the very first time, but these are inherited directly from Calculus 1, the limit laws. Here, the difference is we're talking about sequences, and we insist they're both convergent. That just means the limits exist. C is some constant. And this is just a long list of properties that we just take for granted every time we work with limits. In fact, we've been using these left and right throughout this course. The limit of a sum is a sum of the limits. Same with the differences. A constant times a limit is the constant times the limit. But let me say that a better way. The limit of a constant times a sequence is a constant times the limit of the sequence. Here's the limit law that says the limit of a constant leaves a constant unaffected. Then we have a product rule, a quotient rule, and this one is really about continuity, where the limit goes inside. So again, these are not really formulas that you try to memorize pat. They're just things that you take a look at and say, yes, I was right to take that step. It's supported by that limit law there. So let's just give a overall statement for these. These are properties that we take for granted and should be familiar with. I think when it comes to exam 3, probably just about nobody's going to write down these limit laws. I think the better things to write down would be these kinds of things. This is where the theorems get a little bit more interesting. And I would say theorem 3 is the most powerful theorem in this whole section, because what it's trying to do is connect the fact that our functions have some major difficulties. Let's see, I think we pointed out, yeah, for this function right here, it consists of discrete points, so there is no continuity, there is no differentiability whatsoever. So it feels like we lost a lot of properties and that we're in some kind of wild new territory. But that's not really the case. If that's your sequence, there's an associated function. That function is constrained by those points. It's essentially connecting the dots. And if you take the limit of the function here and get a value, it's the same as the limit of the sequence as well. That one has limit 0, and so does the function if we take the limit as x goes to infinity. So that's the content of our very next theorem. Let's take another look at it. Oh, let me bring this back to the way it was. In our brand new theorem, theorem number 3, it says, if the limit of a function f of x is L, and that function is designed so it equals the value of the sequence at integers n, then the limit of an is equal to the limit of L, where it came from the limit of the ordinary function. So it's a powerful property which now says every limit law that you looked at, worked with in Calculus 1 is carried over here as well. Let's do that to test the convergence divergence of this sequence here. Might need a little bit of additional space. Well, the trouble with this sequence is that as we take the limit as n goes to infinity of n e to the power of n squared plus 1, this thing is indeterminate. Of type infinity over infinity. So that means we want to use L'Hopital's rule on this thing, right? And here's where the work looks really weird. I'm not going to make this the official step, but I just want to make a comment on it. If you write this out, you may not want to copy this down at the moment, but if you wrote it out, it actually isn't totally incorrect, but it is a huge abuse of notation in a certain sense. You might say it's the limit as n goes to infinity of, in L'Hopital's rule, we differentiate the numerator, and we would get e to the n plus n e to the n with the product rule, and 2n in the denominator. But anyone see what makes that a weird statement, differentiating this function? The trouble is, that function, once again, is a sequence. It consists of isolated points. There's no continuity, which means you can't even define differentiability. The derivative doesn't even exist on this thing. Nonetheless, that's not totally inappropriate. You'll notice that the author sometimes does that with a function that's not even differentiable, the sequence. Let's do what the official steps would look like in long form. If this is indeterminate, then the next step is let f of x equal n e to the power of n divided by n squared. Oh, hang on, I made a mistake. I said f of x. I need to be putting in x's. Let me try again. Seem to have trouble with my independent variables lately. So x, e to the x divided by x squared plus 1. So what we've done is that part there. We've defined a new function, and this function here matches the sequence if you put in 1, 2, 3, and so on. It matches at the integer values. You can use L'Hopital's rule on this thing, but you'll notice the steps you take in L'Hopital's rule over here are equivalent to the steps you would take in L'Hopital's rule over here. The only difference is whether you wrote x or n. So if you use L'Hopital's rule right there on a function that's not even differentiable, I'll assume you're thinking in terms of theorem 3. It's actually not something that would lose you points. It is a common abuse of notation. But let's write this out. We define a new function. Because we want to determine if a sequence converges or diverges, the only limit we care about with this function is the limit as x goes to infinity of x e to the x divided by x squared plus 1. This one is also a determinant of type infinity over infinity, so L'Hopital's rule would work. It's equal to the limit as x goes to infinity. Let's work out that product rule a little bit more carefully. I differentiated x to start to just get e to the x. Plus, next we copy x, differentiate e to the x, which is itself. So we got x e to the x plus x e to the x using product rule. Down below that derivative is a 2x. And we're in the same position as before, still indeterminate, type infinity over infinity. This numerator just goes to infinity much, much faster. It surges towards it. This one goes to infinity in a linear way, but still pretty quickly. What that tells us, it's still a L'Hopital rule problem. It's equal to limit as x goes to infinity. We have to differentiate the numerator. So the derivative of that e to the x is itself. We actually differentiate x e to the x. So when we go to differentiate that thing, the total answer is e to the x plus x e to the x. So differentiate there by product rule, and we get plus e to the x plus x e to the x. Any questions so far with those derivatives in the numerator? Okay, the denominator is the fun one. Derivative of 2x just gives us a 2. This is no longer indeterminate because the denominator is constant. This just diverges to infinity immediately. So we found the limit of an associated function that satisfies this property and matches the sequence. And so our conclusion goes this way. We just come back and say, therefore, let's use some color coding here to convey this. We will say, therefore, lim as n goes to infinity of n e to the n squared plus 1 is equal to infinity, and so it diverges. So that's the punchline of theorem number 3. Any questions at all, folks, writing all that out? Okay, I did this in a pretty long way because we defined a brand new function. We took the limit of that function, but my goal is really just to show what theorem 3 is trying to convey, what it's saying altogether. When you go to do these problems and then L'Hopital's rule actually comes up, I would encourage you to do it this way. Just try and figure out where I want my arrow to go. Theorem 3 allows us to use L'Hopital's rule without defining that f of x function. So if you differentiate this, the assumption is you're thinking in terms of theorem 3, and you're working without taking this step right here. Your answers are always equivalent, and that's why it becomes a standard shortcut to take in this situation. But we made a big deal out of it because, once again, it is important to know that that function cannot be differentiated. So when you go to start using L'Hopital's rule on it, it feels like a contradiction occurred, but not really. The thing happening under the hood is there's a new function allowing us to use L'Hopital's rule, even when we're dealing with the sequence. Does that make sense to folks so far for the punchline on that one? Okay, so theorem 3 is huge. It allows us to do weird things with a sequence which is not differentiable. Defining a new function is like the translation layer that makes that correct when you use L'Hopital's rule here. So this is kind of a big march looking at different theorems. This theorem 4 is really conveyed directly out of Calculus 1, but these are always good to kind of remind ourselves about. Theorem 4 says, if your power r is positive, then the limit of 1 over n to the power r equals 0. In fact, that was our first question of these notes. We took the limit as n goes to infinity of 1 over n, and we said it's 0. We were actually working under this theorem right here because the power of that is 1. So r equals 1, which is bigger than 0, which is what we needed for that theorem there. Something I need to just put that down so we don't have to look at it, move up and down. So using this right here, theorem number 4, we can take a bunch of steps to calculate the limit of this sequence. However, if you know the limit of this sequence just by looking at it, by using the method of eyeballing the sequence, realizing it's a rational function in the variable n, you might already know the answer. Let's write it out. Any volunteers for what the answer might be for this one? Exactly. The idea with this is if it's a rational function and you have a tie going this way, the degree of the numerator equals the degree of the denominator, then you are done. Grab the numerator coefficient, the denominator coefficient, and that's the value of the limit. This is really a section 2.4 concept. The concept is that when you take a limit at infinity, that limit only exists if and only if there was a horizontal asymptote. So if you know you're dealing with a rational function, horizontal asymptotes can come up, you can just cite that as your answer. This is going to be a really common shortcut for us because we're going to take limits like this so often when we're in this section of power series, Taylor series, and Maclaurin series, that we don't want to get too bogged down using theorem 4 each and every time. But we're trying to understand theorem 4, so let's do it just this one time. If we took extra steps, well, let's just first convey something. This is a highly recommended shortcut. I feel like I misspelled recommended, but that's okay. Let's keep on pushing forward. But if you took the long form on this, here's what the steps would look like. The limit as n goes to infinity, n squared minus 3n, divide by 8n minus 4n squared. The strategy here to bring theorem 4 into play is you go to exclusively the denominator, find the term with the highest degree, grab the factor that just involves the variable, that's the n squared, and divide everything by n squared. You'll get limit as n goes to infinity, divide that by n squared to get a 1. From here, we'll get negative 3 over n. From here, it's 8 over n. And from here, a negative 4. Next step, we use this theorem a bunch of times. Anything that has a variable in a denominator with a positive exponent goes to 0 in the limit. So that converges to 0. That converges to 0. And all that's left over is 1 minus 0, 0 minus 4. So a negative 1/4. And this thing converges. I meant to say converges here. I think I just totally forgot. So there's a couple ways to do these kinds of problems. This is the highly encouraged way, so you don't get bogged down doing this in the middle of an already pretty long problem. But it's good to do it this way a few times just to see what that's conveying. So that's the big punchline to theorem number 4. Any questions or comments, folks, with that example 5? Okay, well, let's try out another one. Next theorem along the line, theorem number 6. Well, theorem number 6 is helpful sometimes when you have an alternating sequence. Sometimes dealing with those limits is a little bit tricky. And if you want to reason what the limit of this one should be, without having to worry too much if your reasoning is correct, you can involve theorem 6. But one thing to note, if you're determining the convergence or divergence of this sequence, you'd be taking the limit as n goes to infinity of negative 1 power n over n plus 4. And any volunteers for what that should come out as, even if you didn't use theorem 6?
Should diverge to positive infinity. Oh, no.
Yeah, it turns out this one actually converges.
Converges is negative 1 to 4?
Not quite. It's going to come out as something slightly different. But what makes it tricky is definitely that negative 1 to a power, right? Somehow, some way that's baked in. But the critical thing about this limit is if n is going to infinity, sure, you're getting positive and negative numbers, but the denominator is getting ever larger and larger and larger. That's making the absolute value of your quantity get closer and closer to 0 altogether. That means this one should have a limit of 0 altogether. But does that make sense to folks at the moment? It's kind of a tricky limit. So maybe let's back off just one step on this one and see what the steps would go if we did use theorem 6 directly. And then we'll bring in what the shortcut would be when these kinds of things come up. So theorem 6 directly is kind of great. It says, if you have an alternating sequence, then take the limit of the absolute value of that alternating sequence. Essentially, what we're doing is killing off the part that's alternating. So let's begin by writing out limit as n goes to infinity, absolute value of the nth term of the sequence, absolute value of an. This would then, by substitution, turn into the limit as n goes to infinity, the absolute value of negative 1 power n divide by n plus 4. We'll be taking absolute values of things like these quite often. And sometimes it's okay to just do this in one step, but to visualize how it's working, observe that as n goes off to infinity, the denominator is exclusively a positive quantity. So we can rewrite this as lim n goes to infinity, absolute value of -1 power n, divide by n plus 4. So the absolute value bars just center on the part that actually can become negative. Denominator is always positive. And now whether that's alternating or not, if we throw absolute values on it, it's just a 1 now. So now we've got limit as n goes to infinity of 1 over n plus 4. And you know what? That is a rational function. It has a horizontal asymptote, and the horizontal asymptote to that rational function is absolutely 0. The reason being on this one is if you have degree 1 in the numerator and degree 0, let me say that again, degree 1 in the denominator, not numerator, and degree 0 in the numerator, then the denominator now grows without bound, and your quantity gets closer and closer to 0 as n gets larger and larger. So that in the limit, the whole thing is exactly 0. But hang on, the trouble with theorem number 6 is it doesn't fully resolve your question on the first step. We know that by this work, absolute value of an converges, but we have to tie that together with the original sequence, this one. So if you use theorem 6, you need to make another conclusion and say, therefore, the limit as n goes to infinity of an, which was this, you wouldn't have to expand it out, but just to be very descriptive in the notes, this limit, the one that's been alternating, oops, didn't mean to right click on it, weird, is now equal to 0 by theorem 6. And so it also converges. So that's how theorem 6 goes. Any questions at all, folks, with the use of that theorem 6? Okay, here's again another encouraged shortcut on this one. The logic that we made just on this step carries over to the full sequence. So here is a highly encouraged shortcut. The limit as n goes to infinity of the full sequence without us resorting to a theorem is 0, since, let's add some justification because we didn't use a theorem. We might need a little bit extra justification. This is 0 since the numerator is between, let's say in a better way, is either, if I say between, it sounds like it could take intermediate values, but it's either -1 or +1, and the denominator grows without bound. So the highly encouraged shortcut is, if you see stuff like this, where your numerator, it's not constant, but it can't really grow in any direction, it's constrained within a finite range, this always converges at equals 0. The rest of the explanation is mainly for the notes. You wouldn't have to say that each and every time you took a shortcut like that. So that's the major content of theorem 6. It says if something converges absolutely, the original sequence also converges. Any questions at the moment? Sorry, say that part again. So you're saying something that goes like maybe n squared, but like a 4, like that? Well, this one would be a good example where it goes off to infinity. Like you're saying higher power, like in this configuration? Gotcha. So if you have something like this, say, then this one will actually go off to infinity because we have the numerator growing faster and faster than the denominator altogether. Actually, this is a good one to bring down here. Let's take another look at this one. Just as an extra example, we'll take a look at that there. If we took the limit of this one, then again, there's another way to think about this. This is a rational function, but this one does not have a horizontal asymptote. The reason being is the numerator power is too large. So working this one out by the official steps and methods would be take limit as n goes to infinity, n cubed plus 1, n squared minus 1, and we still take the method of going just to the denominator, go to the highest degree term, divide the part that's just the variable part by n squared now. This will be limit, n goes to infinity, divide by n squared here to get an n, plus 1 over n squared. Here this will turn into a 1, minus 1 over n squared. Now, every part that has a power of n in a denominator, where it's positive, this converges to 0 by a prior theorem. You have something constant, divide by something growing larger without bound. But then that part's still alive. We have a positive down below. So as n goes to infinity, that survivor there, that looks like an h actually, let me fix that, goes to infinity on this one. If we reversed it though with n cubed in the bottom, then that's when it would have been a value of 0 in the limit. But this one would diverge. Other questions about that one or the others? Yeah.
So you switch the -1 is like 4, it wouldn't work that way, right?
4 right here.
No, in the very first problem.
Oh, gotcha, up here.
-1 for this theorem wouldn't work.
Correct. Correct. Yeah, with a -4 to power n, now we do have something still alternating, but 4 to power n just grows larger and larger, so this would diverge, correct? So the only reason this worked is this is constrained between -1, +1, but -4 power n would not be. So just to write that in, if it looks like this, now we have something that's totally divergent. I will look into more matters of divergence with a 4 power of n type of a function. That's starting to look more like these kinds of things, the geometric series coming up, although not with the n+4 down below. Part of it's a geometric series. Other questions about that so far? Okay, so lots of little topics to discuss with series, but what it should feel like is rehashing limits, section 2.6 in Calculus 1 specifically, where you're dealing with discrete functions like these things, the sequences. So here's another one. This one is actually really powerful. It's something that comes up a lot. It's something you'll have to use in the formula, in the homework rather. It says, if you know that the limit of a sequence is L, but you have some other function involving your sequence, which happens to be continuous, this is the major takeaway. Continuity with limits allow you to do some pretty amazing things. This is what happens. Because of continuity of the function f, the limit operator can commute inside and give you this out. So if we broke that up into steps, it would really look like this. The limit of an is L. So if we take the limit as n goes to infinity of some continuous function f of an, then the way this could be visualized on paper is it becomes the function with the limit in the inside as n goes to infinity of the sequence an. We were told that the limit converges to L for that sequence an, so we just plug an L right inside here, and it becomes f at L. But that's kind of the key step right there. The limit operator goes inside the continuous function. Sadly, when we write out as a formula, we kind of just skip that step and just say the limit is L. But let's visualize it immediately on this one. If it looked like this, E is gone and it was just 4n plus 3 divided by 2n minus 1. That's just an ordinary sequence. We've dealt with things like that already in these notes. But throwing a function E like that, the base E exponential is your continuous function in this problem. So now when we go to take the limit as n goes to infinity of an, we're taking the limit as n goes to infinity of e to the power, this is kind of hard to even write, 4n plus 3 divided by 2n minus 1, we get this to happen. The limit operator commutes up into the exponent position. We have the base E exponential to the power of the limit as n goes to infinity of 4n plus 3 divided by 2n minus 1. So that's not so bad because we can do this limit right here. The confusion is when you're looking at the whole entire sequence. What theorem 7 allows you to say is the limit affects just this part, the exponent position of that entire sequence. And now that we've gotten there, anyone see the value of the limit? It would be 2, good call. Our shortcut strategy says, look for ties. Sorry, question first. Sorry, which part? Oh, gotcha. It would be any constant, yes. So as long as, actually, now that you've said that, I'm glad you mentioned it. There is some caveats here. What you need right here is an exponential function for this kind of problem. And so b can be equal to, say, let's say it this way. For exponential functions, the base b is always positive, and the base is never exactly 1, or else it's just a really simple function. So any number that satisfies these properties right here would work out just fine. So think like a 7 would work. Other questions about that? Okay, and then coming back over here, we observe that there's a tie in the numerator and the denominator. So we look for the terms. Let me highlight that a little bit better. Oh, no, we can't do that without deleting stuff we want to leave here. There we go. We look to the term that has the power n, numerator, denominator. If this was, say, like an n squared, we would just go to the tie. The limit is formed by taking 4 over 2, which is just a 2, like you said. I'll write in this step often just to show how this shortcut works, but totally fine if you just wrote e squared for the conclusion of that limit. So the limit of this thing as n goes to infinity is exactly e squared. That means this sequence converges. So another convergent one. I think we're running out of theorems, but here's another one that we're going to need. Theorem number 9. Looks like something got skipped. Theorem 8 just didn't seem like a good theorem that we use directly very routinely, but still a good one to take a look at in the reading. Theorems on the notes are the ones that we really need for homework questions, exam questions. And here's the next one. So this goes along with the related comment that was made earlier. What would happen if it wasn't a -1 to the n, but like a -4 to the n or a 3 to the n? Those kinds of sequences get resolved by theorem number 9. Theorem number 9 says the following. A sequence like r to a power of n is convergent as long as your base r is strictly bigger than -1 or less than or equal to +1. And moreover, if you have your values here so that it is a convergent sequence, this is the result. If r is constrained between -1 and +1, you get a 0. And if r is exactly 1, you get just a 1 out. So this is actually a pretty important sequence because that sequence right here, r to the power of n, is a component to the geometric series. The geometric series gets tied up with that thing, where we have r to the power n-1. So let's take another look at this just to get a feel for what's going on with it. Excel is going to be used only for the sake of visualization when we're dealing with a sequence or series. Never something you have to use in a homework setting, just a tool for class. I'd use Desmos, but I'm just not good at plotting sequences in Desmos. So here we put in the index n. This is the sequence an. Let's put in just a good number of terms. Nothing too outrageous. Let's go from here down to 18 of them. Why not? Or I guess that's 17 terms. And now what I'm putting in here for an is that function there, some common ratio r to a power of n. You have to come up with a value. Let's say 0.5 to start. The power n up here is the index. So it's the value over here to the left. So I should write, forgot how Excel works again, equals 0.5 to the power of A2, the index to the left. So this is what all the terms of the sequence would look like. But if your sequence starts with r is 0.5, when you plug in 1, you get 0.5. When you plug in 2, you're taking 50% of 0.5. And the values just get smaller and smaller until we're in scientific notation all of a sudden. Let's see if we can visualize that one real quick. So it becomes a clearly very, very convergent sequence. However, let's take a look at this theorem. It says it's convergent when you're in this range, and that's not a typo. It's kind of funny how it's unbalanced, right? What goes wrong at -1? Well, if you put -1 here, to the power of, oh, God again, equals -1 to the power of this value to the left, double click to update everything, then this is what you're left with. It turns into a sequence where you get either a +1 or a -1, and this is divergent because the dots are not getting close to anything, like it was in this example. Here, the dots were getting closer and closer to 0. And in the function, it says if r is between -1 and +1, the limit of that is always 0 altogether. So that's what goes off on -1. It just turns into an alternating sequence, +1s, -1s, and nothing else going on. What happens at exactly 1? That's a boundary value where the limit comes out as 1. That's just because 1 raised to any power is still just 1. Let's do it just because we can. So here's 1 raised to the power 1. For this one, that's 1 raised to the power of this value, A14, which is 13. But all you get is this. It's just a sequence of 1s, so clearly it converges and must equal 1. So the interesting cases are really these right here. And every time you deal with this kind of sequence, the limit is 0 in that range. Does that make sense to folks with the visualization and the formulas there? Okay, now we want to determine if this thing converges or diverges. It's unfortunate because a lot of times when you go to use theorem number 9, you're given stuff where you can't use theorem number 9 directly. You have to do some exponent surgery to that thing before you even get started. So before we even think about convergence or divergence, let's work on this thing right here. We're trying to come up with a common ratio r to some value n. So the way to make that happen is 4 to the power of n+1, the power has to decrease. So we factor out one factor of 4. 4 times 4 to the power of n is divided by -5 to the power of n. And from here, we can combine our bases. If you have bases to the same exponent, then this can be rewritten as 4 times 4 divided by -5 to the power n in that kind of way. The reason that works is if you go backwards, if you raise a fraction to a power, you're just raising the numerator and denominator to that common power. So if you have a mismatch with exponents, do some factoring, then you can reconvene into something like this. Next, we take the limit as n goes to infinity of an, which is the limit as n goes to infinity of 4 times -4/5 to the power of n. Let me fix that 5. Because we're thinking in terms of limit laws, you might not be too happy with this thing, because this formula describes something to a power of n without a constant in front of it. We have a constant, which feels like it throws it off, but that's the purpose of the limit laws. The limit law says you can take certain things for granted, and this is one of them. 4 as a constant moves in front of the limit. So now we're back to this kind of limit, which is now compatible with the definition here. Our value of r equals -4/5, which is between, that's probably not the best way to convey it. R value of -4/5 means r is between -1 and +1. I think that's a better way to say it, because it reminds us we're in this situation. And so the whole limit comes out as a 0, and that tells us that this one converges. Any questions about that one there, folks? This one's pretty weird again because of the exponent laws. But once we get down to it, all we needed to find out was what is the value of r. We got it right at this stage. Really, we got it at that stage there. And the moment we found it, it is larger than -1, we had a limit of 0 automatically on this kind of thing. If it was a reciprocal, say -5 divided by 4, then it doesn't fall in this range. The whole thing would just diverge. Any last questions, folks, with the theorem number 9? Yeah.
On the homework or whatever, we do if r was -1, would you just want us to say that it's divergent since it doesn't really have an answer to it?
Yeah, just say divergent, and that's a great way to write your answer. There are some shortcuts, but they're not totally standard. Some shortcuts go like this, or shorthands rather. If you take the limit as n goes to infinity of -1 to the power of n, I would say the best answer is just diverges. But if you like shorthands, you could say or lim as n goes to infinity, -1 power of n is positive or minus infinity. This is one of those kinds of shorthands where you might want to ask your instructor if you're in a different class if that's acceptable, because people have strong opinions on those kinds of things. Some people like it and feel it's appropriate. This is a real debate because if you go -1 to the power, oh, forgot the equality again, -1 to power of n, or excuse me, I was thinking of something slightly different, -4 to power of n rather. That's the n power. I was thinking of something that goes along these lines. Oh, hang on, I think I have a weird problem in my notes here. No, that looks about right. Yeah, it's just diverging in a funny way because these last two terms are really, really large. I think it's just hard to see the graph on that. Let me try just doing the first 5 terms. That's about right. Some terms are going to -infinity, some terms are going to +infinity. I was having the wrong thought on this one. I was thinking -4 to the power of n on that. So that wasn't quite the question you were asking. But if it's -4 to the power n, some of the terms are getting large negative, some are getting large positive. So that's an appropriate shorthand. But the question you were actually asking was this, lim as n goes to infinity, -1 to n diverges. Or some people might say lim as n goes to infinity, -1 to the power of n is positive or -1. Again, these are not always the best shorthands, but if it makes sense, then it's not too bad a thing to say. The better answer is just diverges to both of these here. They diverge for particular reasons. This one's shooting off in 2 directions. Some terms are getting large positive, some terms are getting large negative. But this one's diverging because the terms are just never settling down to anything. They're just purely alternating between a positive and a -1. But lots to say about this kind of stuff.
By observing that it's going positive and -1, can't we say it's an average of 0?
That'd be another way to say it, but the limit never actually hits zero, so we couldn't say it converges to zero. We're just saying that it's oscillating between the two, and yeah, the zero is the average value in the middle. So that wouldn't be a bad thing to convey it as well. But in the end, either way we say it, all of these are still just diverges in the end. Does that make sense so far, folks, with these additional questions? Okay, well, we've got about 6 minutes and some change. For example 4, all I've got going on is just a few more random sequences, no longer theorem, problem like we've just been getting through. This time the problems are kind of uncategorized, and we just have to decide what to involve on each one of these kinds of things. So this one's a little bit odd. It's a factorial function, which just seems like an oddity. For example, if you write something like 3 factorial, that's just a shorthand of 3 times 2 times 1 for a value of 6. Curiously, it's tradition to put the times 1, even though times 1 doesn't affect the product. If you write n factorial, then you could write that out as n, just like here. 3 factorial first involves a product of 3, then 1 less. So it's going to be n minus 1. Then we go 1 less, so n minus 2. We don't know how big n is because it's unspecified, so we convey the rest of it by going dot, dot, dot. 3 times 2 times 1, assuming n is larger than 3, for example. So that's what would happen to n factorial. Any questions so far about the factorial function? Okay, again, factorials, they probably didn't seem like they fit a really big role in mathematics, except maybe counting, combinatorics, probability, it comes up. But it actually comes up in calculus in a super surprising way. You'll need factorial functions when we're dealing with power series. So that means we need to get a good handle on these kinds of things because they come up in a legitimate way. So let's take another look at n factorial. This is just one way to write it. You could also write n factorial equals n times n minus 1 times n minus 2. And instead of writing everything out, you could just end it right there. N factorial could be expressed in this way: n times n minus 1 times n minus 2 factorial. If we do an example with an actual digit, we would say something like 5 factorial is 5 times 4 times 3 times 2 times 1. But you could also say it's equal to 5 times 4 times, well, 3 times 2 times 1 is 3 factorial. And that's an appropriate thing to do. Sometimes we need to do things like that if we're simplifying a function like the one down below there. So just for another example, if you write something like maybe 2n plus 5 factorial, this one could be broken down as 2n plus 5, 2n plus 4 factorial, or we could have kept on putting in more and more terms and then end that factorial, or we could just go down the whole total line. It just depends on the context. So for this one, looks like our last problem for the day, we could break this down as, if it's a 2n plus 3 factorial, that means you take 2n plus 3, you're going to multiply it next by 2n plus 2. But right here, we should stop and not keep on listing out terms because we already have a 2n plus 2 factorial down below. So all I've done with this one is start at 2n plus 3, write it in, go 2n plus 2 with a factorial. Much like with these examples here, we just stopped at that spot. Denominator is 2n plus 2 factorial. So that means the sequence an is really just 2n plus 3 and nothing else. We can take the limit of that. The limit as n gets larger and larger of an is now the limit as n goes to infinity of 2n plus 3. But if you take the limit as n goes to infinity here, well, we're just going to infinity as well. So this whole thing diverges. So this is a really oddball problem, but we're looking at some of these weird little nuance things like dealing with factorials early because they come up down the line We wouldn't want to see this for the very first time when we're in section 11.10, for example. That would not be a good service to us. So the whole punchline to example 4 was part A was just dealing with the factorials. Any questions at all, folks, about that one? Okay, and with what we have on the last bit of these notes, again, we'll come back on next class to finish this off. There's just a couple more sequences to take a look at and analyze the limits on. Looks like part B is going to require properties of logarithms. And part C, who knows what this requires. We'll take a look at that and give it our best shot once we get there. I think this one ought to converge. This one looks like it's a divergent one if you're curious to know. But I think this will be a good stopping point for us, folks. We'll come back next class, finish this off, move into a series next. Any last questions whatsoever? Okay, well, have a great night, everyone. And we'll finish off midterms week with some more of this stuff.